Okay, I believe this might be our last video. There might be one more. So, applications of derivatives day 3. Remember that this was, that's going to bug me. There was no space there. Excuse me. This was the notes from the derivatives packet. So we had started these on page 36 from the derivatives, not the applications of derivatives. We had gone through and done some examples, remembering that the key to this is similar to implicit differentiation. We use chain rule when it seems odd to use chain rule, but if we think about the application of it, it isn't odd, and we're going to go a little deeper into that. So, steps used to solve related rates problems. Read the problem carefully. I mean, we always have to do that, right? That should go without saying. Write down the quantities that are given and identify what the question is asking using the appropriate notation. Make note of any quantities that are constant. Okay, so let's look at this. Excuse me. If the volume V of a sphere with radius r expands as time passes, find dv dt in terms of dr dt. And that volume formula isn't in your notes. I wrote that down. That volume formula will be given to you, even on an AP exam. So, sphere, cone, what else is a common volume or solid that they give you formulas for? They won't give you a formula for something like a cube. You need to know how to find the surface area and volume of a cube, or a rectangular prism, for example. Excuse me. I'm trying to think if I've ever seen a cylinder question. I don't believe I have. I don't know if they would give you a formula for a cylinder or not. But, all right, so read the question carefully. I did. Write down the quantities that are given. Well, there's no quantities given. There are no numbers for this. The question is asking for dv dt. Oh, my pen is not on. Okay. The question is asking for dv dt, and it says in terms of dr dt. That means there's going to be a dr dt in your answer. Okay, so the derivative of v, right, with respect to time, I'm going to leave that 4/3 pi hanging on for the ride. That's just a coefficient. That should say cubed right there. The formula is cubed. It's a 3-dimensional solid, so the formula has to be cubed. Or there has to be degree 3, I should say. And then I'm going to multiply by the derivative of the r, but I need to keep in mind that the r also has a rate of change. Imagine a ball or a balloon that's perfectly spherical. If I'm increasing the volume by blowing air into the balloon, the radius is changing. There's no way for the volume to change without the radius changing. So the radius needs a rate of change as well. Okay? And then, and that's it. So this is a pretty straightforward, we probably could have done this in the last video. You've done this before, actually. We recognize that the change in volume is the same as the surface area with respect to the rate of change of the radius. All right? Okay, so here's where we're going to start following some steps. Write down given information. So dy dt, y is changing with respect to time. And then when... actually, no, I'll write it like this. When y is equal to 4, they want me to find dx dt, okay? And then they have the formula. So I read the question carefully. I wrote down pertinent information. There are no constants. You'll see that in a bit. Draw a diagram and label if possible. I mean, there's no diagram. So there's two things that this could look like. I could think of this as a circle with a radius of 5 centered at 0, 0. So these would be 5, and the center is at 0, 0. So like if I'm changing the x, then the y is also changing if it's going to continue being a circle, right? I'm going to leave it at that. Okay, so you'll see the draw diagram in a better example in a bit. Write an equation or equations that relate the various quantities of the problem. Okay, so that actually, we're still not into like the big, I don't need these steps yet. I don't know why I wrote them above these two problems. We could have done this problem last time also. So I'm going to take the derivative, and you might be tempted to do this with implicit. Okay, don't write this down yet. Oops, don't write this down. Okay, so first thing you got to notice, it's asking me to find dx dt. If I do this like an implicit problem, I can't find dx dt. There's no dx dt. Okay, so these problems are clearly going to be related rates problems, and they are clearly going to tell you what needs a rate of change. You'll notice that these are dx dt and dy dt, so everything is changing with respect to time. Time is passing as these figures and solids expand and compress. Okay, so everything needs a rate of change, and then I can just start plugging in. So I have, that's probably not a good color to use. Dy dt is 6, so I'm going to put that right there. I know that y is 4, so I'm going to put that right there. And I've got the 2 in front. Dx dt is what I'm trying to find, so I'm going to leave that. I've got the 2 in front. But what about the x? It doesn't tell me anything about the x. So here's where I need to take a separate step. I need to go into this equation to solve for x. I'm going to write it that way so you can see this is clearly a 3, 4, 5 triangle. 3, 4, 5 triple, I should say. It's kind of a Pythagorean theorem problem. So then I can use that 3 right there, and I can go, what is this? 6 dx dt plus, you know what? I'm not even going to do that. This is what I'm going to do. I'm going to divide everything by 6. Divide by 6, divide by 6, 0 divided by 6. So I just have dx dt plus 8 equals 0. Dx dt equals negative 8. And there's no units for this. So I can't put units in the answer. I don't expect you to put units if there's no units in the problem. Now, think about this. If this sum is equal to 25, and the dy dt is positive, meaning that the y value is increasing, then the dx dt has to be negative. There's no choice. If the sum is staying set at 25, then if y increases, x has to decrease, and vice versa. That's an interpretation of what's going on there, okay? All right. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? And again, that formula will be given to you. So read the question carefully, write down any pertinent information. Always label the pertinent information. So it tells you right here its volume is increasing. You can also see that this is clearly a rate of change of volume because it's cubic centimeters per second. So that is telling me the change in volume with respect to the change in time. Match up your units. How do I want to do this? This is a volume, and this is a time. That needs to match up, okay? How fast is the radius of the balloon? Didn't need to do that. Increasing. So the question is asking for dr dt when the diameter is 50 centimeters. So we have a problem now, right? We have a diameter given, and it's asking about a radius, so we're going to fix that problem by just saying if the diameter is 50, then the radius is 25. Okay, now, I can't start plugging stuff in. Let me see, I bet it's up here. We haven't gone through these steps. Okay, so write down the pertinent information, draw a diagram, and label. So, I mean, I have a sphere. And air is being pumped in, and the radius is then going to be expanding. There's not much we can draw for that. Write an equation or equations that relates the various quantities of the problem. This is the step where you may need to substitute or use similar triangles as in the optimization problems, which we haven't learned. So the formula is given in this one because it's a volume of a sphere, so that pertinent formula, or however I said that, would be given. We're not talking about similar triangles yet. You cannot substitute quantities into equations here unless they are constants, things that are not changing. Everything is changing in this problem, the volume and the radius, so I can't substitute yet. Differentiate both sides of the equation with respect to t. So I need to take the derivative with respect to t. We already did this one above, so I'm not going to re-show the work on that. Okay? So take the derivative with respect to t. Substitute the numbers that are not constants and solve for the unknown rate. So 100, the change in volume, I'm going to start plugging in. Sorry, I just got distracted for a second. Okay, so the 100 goes in for dv dt, 4 pi r squared, and then dr dt is what I'm trying to find. I'm going to show you some math teacher magic. I've got 100 on both sides. You're like, no you don't. Yes I do. I'm going to divide both sides by 100. Yes, that's what I just did. Because 4 times, so that's 25 squared, right? So 25 times 25. 4 times one of those makes 100. So I end up with, I can just go 1 over 25 pi. If that just completely blew your mind, please just simplify that. I'm 100% sure you can simplify that if you multiply the 4 times the 25 squared and then divide both sides. I promise you. Okay? So now the radius is, oops, I got ahead of myself, is increasing at a rate of, what is it, 1 over 25 pi. So now the units for volume were centimeters cubed per second. The radius is going to be measured to length. So it's centimeters per second. At the moment, when, what did they give me? The diameter is 50 centimeters. Okay. Now, if I plugged in a different number, let's say if the diameter was 100 centimeters, I would be plugging a different number in. That's really loud. That's fun. I would be plugging a different number in there, right? So at a different time, when the diameter is 100 centimeters, I'm going to get a different rate of change for the radius. So in these problems, I want these answers to look like this. This is a formula. I want you to understand why we write it that way, but I need you to say whether the thing we're looking at is increasing or decreasing, the rate that it's changing with units, and at the moment when, blah, 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 whatever was given in the problem. Okay? All right. A man starts walking north at 4 feet per second. Wait, let me make sure that we did everything in the... Write a complete conclusion statement up to the same standards as the last section. So I just told you what those standards were. Okay, so we went through everything in that. All right, so we're going to extract information and draw a picture. Those are steps 1 and 2. A man starts walking north at 4 feet per second from a point P. So, whoop, that's my highlighter. So there's some point P, and a man is walking north, and his rate is 4 feet per second. Okay. 5 minutes later, a woman starts walking south at 5 feet per second from a point 500 feet due east of P. Due east, 500 feet. She starts walking south, and her rate is 5 feet per second. Did I miss anything? Let's not forget the 5 minutes later, because that's important. At what rate are the people moving apart 15 minutes after the woman starts walking? So they're actually talking about the rate of change of this thing right here. Okay? Now, there's no way to do this with two triangles because there's no way of knowing how long this segment is relative to this segment. There's no way. Okay? So you're like, well, then what do? We make a bigger triangle. We think of a triangle. This is what we're trying to find the rate of change of. So we need to keep that in our picture. Okay? We know the rate of change of this and that because that matches what's across from it. And then we know the length of this, so we have ourselves a right triangle. So, trying to save space here. I'm not going to draw it quite so large, okay? So not quite to scale, but I have a right triangle. I know that this is 500 feet, right? And then I know this is what I'm trying to find the rate of. So if that's called z, then this is dz dt, and that's what I'm trying to find. Okay? So I'm going to call, let me use some different colors here. I'm going to call this length from here to here x. So then this is the rate of change of x. And then I'm going to call this length y. So then this is the rate of change of y. Okay? I don't like the way that looks. Hold on. I don't want it to look like that y is attached to the 5. The length is y. The rate is dy dt. And that's